So now we shall begin the second week of this program, and we begin with this chapter on Laplace transforms. This is perhaps the most important topic in this entire course. So the title is Laplace transforms, chapter 5, right? It's Laplace transforms. All right. So let us begin with the definition of a Laplace transform. We need to define a certain class of functions for which the Laplace transform exists, and I am going to refer to this class as the class of Laplace transformable functions. So what are the conditions that are required of a function for the Laplace transform to exist? That is the first thing that we have to deal with. So let us discuss functions of exponential type. Now we shall always have a function f defined on the interval 0 to infinity, taking real values. So we shall assume, given such a function f from 0 to infinity to r, such that for every t bigger than 0, integral 0 to t mod f t dt exists either as a proper or an improper integral, right. So the function is defined on the interval closed at 0 all the way up to infinity, a real valued function defined on 0 to infinity, 0 included. Now it could become unbounded, let us say at 1, for instance. We could, for example, look at f of t equal to 0 when t is between 0 and 1, and from 1 to infinity it could be 1 over square root of x minus 1. This function is defined on 0 to infinity, but at the neighborhood of 1 it is becoming unbounded, but nevertheless the improper integral exists. If you take, let us say, 0 to t, then it is basically integral from 1 to t, because between 0 and 1 I had defined it to be 0, and 1 over root of x minus 1 from 1 to t exists as an improper integral, correct. So the function can really become infinite in neighborhoods of certain points, and we do not want too many such points, right. We do not want it to happen at every rational number, that would be unpleasant. On the other hand, we do not want to put in restrictions like, oh, this behavior should only be should happen only at finitely many points. Well, that would then rule out things like root tan t into e to the power minus t. They are nice functions, they also appear, right. I mean, root tan t into e to the power minus t, square root of mod tan t, put a modulus sign so that the square root becomes a real square root. And this function will become unbounded at pi by 2, 3 pi by 2, 5 pi by 2. So these singularities are evenly spaced out. This is also a nice function. You do not want to rule out such things. So you need to be a little careful in defining this. You should have a fairly broad class of functions, and also they should have some decent behavior at infinity. Now this tan t e to the power minus t will not be well behaved, because it is becoming unbounded at every at a whole bunch of points going off to infinity, that you do not want that also, right. So let us just say that we want integral 0 to t mod f t dt to exist for every t positive, either as a proper integral or as an improper integral. That is the first condition. Let us put a second condition. The second condition is of a different nature. It is a growth condition at infinity. That is, the function does not grow too rapidly. E to the power t squared, surely it is a continuous function, so its integral from 0 to t will exist as a proper Riemann integral. But then the function is growing much too rapidly. We do not want that, correct. So we want some condition like mod ft less than or equal to a e to the power omega t. We are going to put some such condition, namely the function should be dominated by a exponential function of the form e to the power omega t. So, e to the power t squared is out, e to the power t squared will not satisfy this condition over here. It will not satisfy the condition mod f of t less than or equal to a e to the power omega t. So, is it clear? So, we make two conditions that the over finite intervals the integral of the function should have a finite integral, mod of f should have a finite integral, and a growth condition in infinity. These two put together, let us call such a function satisfying these two conditions as a function of exponential type, alright. So, for this function of some number of examples can be given for functions of exponential type. Do not write all these examples, they are obvious examples. 1 over root t is of exponential type. Cot pi t is not of exponential type because you cannot have an inequality of this kind, f of mod f of t less than or equal to a e to the power omega t. This inequality will fail, right, in a neighborhood of 0, 1, 2, 3, in the neighborhood of all the integer points, this kind of a condition will fail. So, the growth condition is not satisfied. T to the power a is of exponential type for every a bigger than minus 1. This is easy to see. E to the power t squared is not of exponential type. This is an exercise. Is sin t upon t of exponential type? It is of exponential type because at the origin it is continuous, and so the integral of sin t upon t from 0 to t is a proper Riemann integral. It is not even an improper integral, it is a continuous function actually. At the origin you define its value to be 1, and so everything is nice, and as you go along the thing is actually going to 0 as t tends to infinity. So, it is surely of exponential type. Exponential type allows you the exponential growth, the function can become infinite. E to the power t is of exponential type, e to the power 2t is of exponential type, sin t into e to the power t is of exponential. Function can grow at infinity, but the growth should not be faster than an exponential function. That is what it is. It should not be super exponential like e to the power t squared, e to the power t cube, etc. Gamma t will not be of exponential type, right. Gamma of n is n minus 1 factorial. It is growing too rapidly. It is super exponential. Gamma n plus 1, right. To look at the Stirling's approximation formula, gamma x plus 1 is x to the power x into e to the power minus x. And what is x to the power x? E to the power x log x. That is too big, that log x is there. It is not e to the power ax. Had it been e to the power ax, we are fine. That a should be a constant, but in the gamma function case, it is e to the power x log x. Not allowed. So, it is not of exponential type. So, let me just put that also as an exercise. What about gamma t plus 1? I have already given you the answer. It is not of exponential type because its growth is like t to the power t, e to the power minus t, square root of 2 pi t. Stirling's formula tells you that it grows like e to the power t log t minus t. That is too much. Okay. All right. So, we have examples of functions of exponential type, we have examples of functions that are not of exponential type, and the class of functions of exponential type is quite rich. Functions can grow. Now, if f is of exponential type, we define the Laplace transform of f to be the integral 0 to infinity e to the power minus st f of t dt. Please write down the definition. Just write down the integral. Laplace transform of f equals integral 0 to infinity e to the power minus st f of t dt. Just write that, right? Just write just the definition. That's all. That's all that you really need. Correct. Now remember that we are assuming that the function is absolutely integrable on 0 to t. Correct. And so it is easy to show that for a functions of exponential type, the Laplace transform will always exist. Okay. Right. All right. So what is the story now? What is the Laplace transform again? The Laplace transform of f is integral 0 to infinity e to the power minus st into f of t dt. What is it? It is a superposition of exponentials. It is a superposition of exponentials. It is a continuous superposition of exponentials. It is not a discrete superposition. It is not like C1 e to the power 2t plus C2 e to the power minus 2t. It is not that kind of a business. It is a continuous superposition, and when you are taking continuous superpositions, you should take a density function. Correct. Once again, the Laplace transform of f is integral 0 to infinity e to the power minus st f of t dt. This is nothing but a continuous superposition, a continuous linear combination of exponentials. The exponentials are e to the power minus st. E to the power minus st is a function of t, and it is a family of functions, right. S varies over the real line, right, or a part of the real line. S varies over an interval, let us say. S is a continuous variable. So you are having a family of exponential functions, a continuous family of exponential functions, and you are trying to take a superposition. And in order to take a continuous superposition, you have to take a density function, and you are integrating with respect to the density function. So f of t is the density function, and you are taking a continuous superposition. I mean, if you take a discrete superposition, right, C1 cos x plus C2 sin x, the C1 and the C2, the number, the coefficients will give you information about the amplitude of the oscillations, right. If you think of it as a signal, the power of the signal, right. So the density function gives you the amplitude, distribution of the amplitudes. So frequently I am going to denote the Laplace transform by capital F of x. So the function is little f, its Laplace transform will be denoted by capital F, and sometimes we shall use script L f also. So typically the functions will be little f, little g, little u, and the respective Laplace transforms will be denoted by capital F, capital G, capital U. The variable for the original function will be little t, and the Laplace transform will be a function of s. This is a convention. This is a convention that is always followed, universally followed, and we will also stick to the convention. Okay? And the Laplace transform will be defined on some interval of the form omega to infinity. If the function is of exponential type, then there is an omega appearing, right, in the definition of functions of exponential type. The Laplace transform will then exist on the open interval omega to infinity, because the integral will converge on the open interval omega to infinity. Clear? It's time for a few examples of how to calculate Laplace transforms. Take the simplest example is exponential function e to the power at. You can compute the Laplace transform of e to the power at. Directly you calculate, it is 1 over s minus a. Directly you calculate, it is 1 over s minus a. Remember, I am assuming that a is a real number. I am assuming that a is a real number. Correct? What happens when a is complex? We shall see later. Laplace of 1 is 1 over s, Laplace of t is 1 over s squared, Laplace of e to the power at is 1 over s minus a. Please write these three things down. And as you see, script L is the symbol used for Laplace transform. Laplace transform of f is simply denoted by script L of f. Correct? These are very easy to check. You please check it. All right, shall we proceed? Quickly, just write down just the relevant formulas. No need to write down the full text. Yeah. Right. All right. Next, Laplace transform of t to the power a. Let us calculate Laplace transform of t to the power a. A is again real. I am assuming that a is real. We will wait for a complex. We will see examples when a is complex. No, don't worry about it. Take first the case when a is real. Integral 0 to infinity e to the power minus st t to the power a dt. Okay, put st equal to u, all right, and then it is e to the power minus u by s to the power a du by ds. It is 1 over s to the power a plus 1 into integral 0 to infinity e to the power minus u to the power a du, which is gamma of a plus 1 upon s to the power a plus 1. So, in the computation of the Laplace transform, we directly see the gamma function appearing. The result obviously holds for complex a as well, because the substitution that we have made is st equal to u. S is real, t is real, and u is real, right. Remember, the substitution that we are making is st equal to u, and so the result obviously holds for complex a as well. What is the matter? Not clear? See, what is t to the power a? E to the power a log t, right? It has a real part and an imaginary part. The function is complex valued, but the input is a real number, no? It's a function of t. And you are making, so suppose you take a function f, which is a complex valued function, it can be written as g plus ih. So what is integral of ft dt? It is integral of gt dt plus I times integral of ht dt, correct? And what substitution you are making? St equal to u. You make the same substitution in the g integral and in the h integral, and everything will go through, right? That is why here we started out with a real. Always begin with a real, and then we will see what happens at the end. Okay, whether it will hold for complex numbers also, that has to be examined carefully. Reason why we have to examine it carefully, you have to look at the mechanism which was involved in arriving at the answer. Here there is nothing weird going on. It's a straightforward scaling in the variable st equal to u. You are simply scaling the variable t. It's a scaling transformation, and the scaling factor is s, and that s is a real number we are assuming here, correct? So that's why there is no problem. Okay. Now let us go to the next example. Integral 0 to infinity e to the power minus st e to the power at dt. The Laplace transform of e to the power at is written down. Here how will you arrive at this answer 1 over s minus a? Again the answer is 1 over s minus a. What is the, how do you get this It is integral 0 to infinity e to the power minus t into s minus a, correct? integral 0 to infinity e to the power minus t into s minus a. What are you going to do? You are going to put t into s minus a equal to u. If a is real, then this is a simple scaling, and the scaling factor is s minus a. But if a is a complex number, then this is not a real substitution, this is becoming a complex substitution, no. If you put t into s minus a equal to u, this change of variables is no longer taking place in the real domain. Now we are doing something funny which you have not done before. Our change of variables formula that you have proved was in the real domain, but now you are making a complex substitution. So the validity of the formula is suspect, correct. That is why I say that the result integral 0 to infinity e to the power minus st into e to the power at dt equal to 1 over s minus a was proved for real a. This result also is true for complex a, but now it is not obvious. Whereas in the other case, Laplace of t to the power a equal to gamma of a plus 1 upon s to the power a plus 1, there also we assumed a is real, but it is obvious that the result is true for complex a because the proof goes through. Why? Because the change of variables is real, st equal to u, there is no problem, s is real, t is real and u is real. Whereas here, if you try to put t into s minus a equal to u, you are making a change of variables which is not legal, correct. All right. So now let us look at a simple case when a is purely imaginary. Let us look at the case when a is purely imaginary. I am going to hide a part of the slide. Here it is. Let us take a to be I omega, e to the power I omega t. What is e to the power I omega t? Cos omega t plus I times sin omega t. Laplace of taking the Laplace transform is a linear transformation. Because the integral, it is an integral, right? Integral is a linear operator. So Laplace of cos omega t plus I times sin omega t is Laplace of cos omega t plus I times Laplace of sin omega t. So to calculate the Laplace transform of e to the power I omega t, I have to calculate individually Laplace of cos omega t and Laplace of sin omega t. What is Laplace of cos omega t? Integral 0 to infinity e to the power minus st cos omega t dt. Laplace of sin omega t is integral 0 to infinity e to the power minus st sin omega t. These two integrals can be calculated using method of integration by parts, correct. The formula comes out s upon s squared plus omega squared 1 over s squared plus omega squared. Please write down these two formulas. Laplace of cos omega t is s upon s squared plus omega squared, and Laplace of sin omega t is 1 over s squared plus omega squared. Please write down these two formulas, and you have to check this by integration by parts, correct. Now integration by parts is going to be messy, correct. E to the power minus st cos omega t, we will have to integrate by parts twice, right. Omega upon s squared plus omega squared. Thank you very much. Yes, absolutely correct. It is Laplace of sin omega t is omega by s squared plus omega squared. Now when you want to prove these formulas, you want to prove them by, you have to prove them by integration by parts. You will say integration by parts is boring, we have to do it twice. So why not be smart? Why not just write cos omega t as 1/2 of e to the power I omega t plus e to the power minus I omega t, and compute individually the Laplace of e to the power I omega t and the Laplace of e to the power minus I omega t, and add the results. That would be the shortcut, correct. So what is Laplace of e to the power minus st into, what is the integral of e to the power minus st into e to the power minus, plus or minus I omega t? You write it this way, look at the last line, it is integral 0 to infinity e to the power t times minus of s plus I omega, or, and is tempting to write, it is tempting to write e to the power minus st into e to the power I omega t as integral 0 to infinity e to the power minus t into s minus I omega, put t into s minus I omega equal to u, correct, and you get integral 0 to infinity e to the power minus u du upon s minus I omega, right. T into s minus I omega is u, s minus I omega is a constant. So dt will be equal to du by s minus I omega. So put it in, and what do you get? 1 over s minus I omega. The other piece will give you 1 over s plus I omega. Combine the two, you get s over s squared plus omega squared as a Laplace transform of cosine of omega t. Now you will say that this is much easier than repeated integration by parts. But here we have now made a change of variables which is illegal. Result is correct, result is absolutely correct, but it is an illegal change of variables. So here is a little warning, the final result is correct, but the change of variables t into s minus I omega equal to u is wrong. The way to perform such a complex substitution is via the Cauchy integral theorem. You have to use the, you can make the change of variables formula, but not directly, in conjunction with the Cauchy's theorem in complex analysis. That is a correct way to do it, and we shall see the correct way to do it in a few minutes, but let us go further. We will see what the problems are. We shall analyze why complex change of variables can give you wrong results. That problem, I have spent a few slides on explaining this matter. It is very important, you must tell your students this, because there will be smart students in your class who want to do this, and you must point out the seriousness of the situation. It can lead to serious pitfalls. It is mathematically incorrect as it stands, it requires justification. And how do you justify it? How do you fix up the gap, or how do you correct those errors is something that we should know, correct. So making complex change of variables is a serious business. Mind you, books make this mistake. There are books where they do this, they say put t into s minus I omega equal to u. I can tell you several books which make these mistakes, so please be warned. We shall look at other examples in the tutorial class if you like. We can spend more time on this in the tutorial class. So the advice is the Laplace transform of cos omega t equal to s upon s squared plus omega squared should not be derived from the pair Laplace of e to the power I omega t and Laplace of e to the power minus I omega t, unless you first prove this result using Cauchy's integral formula. more, instead of doing star, let us do the general thing. If you are going to do it using Cauchy's integral theorem, why just stop at this special case? Let us do the general case. Let us prove that the Laplace transform of t to the power k e to the power at. Let us compute the Laplace transform of t to the power k e to the power at, where a is a complex number, correct. At the moment you can assume that k is a non-negative integer. At the moment you can assume that k is a non-negative integer, or you can assume that k is a positive real number. Let us for the moment assume that, and then it will become very clear how to generalize that further. Okay. So, begin by assuming that k is a non-negative integer. So, let us not complicate matters, let us assume that a is complex and k is a integer, alright. So, what is the Laplace transform of t to the power k e to the power at? Integral 0 to infinity t to the power k into e to the power minus t into s minus a dt. Now, please give your full attention, do not spend time writing this. This will be there in your Moodle very soon and you can have it for yourself. So, here your attention is more important than records in your notebook, alright. This is a difficult matter, this is a serious, this slippery business, very slippery business. Please give your full attention. Let us assume that s is bigger than real part of a. Let us begin by assuming that s is bigger than real part of a. So, the vector joining the origin and s minus a lies on the right hand side, points to the right, right. Your a is here and s is to the right of a. S is bigger than real part of a, that means s is lying on the right of a. So, the vector joining the origin and s minus a, the position vector of s minus a basically points to the right. Is that clear? It may be in the first quadrant or in the fourth quadrant. Let us assume it is in the first quadrant. The argument is similar if it is in the fourth quadrant, right. So, the picture indicates an s minus a in the first quadrant. So, now let us take the complex valued function f of z equal to z to the power k e to the power minus z. That is an analytic function. E to the power minus z is analytic on the whole complex plane, and if k is a non-negative integer, z to the power k is also analytic, it is a polynomial. So, f of z is a entire function as it is, as normally referred to. A function which is analytic in the entire plane is called an entire function. So, now let us apply, let us consider a sector at the origin and which consists of the real axis, a circular arc, and back to the origin along the other arm. The sector has two arms, right, the arms of the sector and the circular arc. So, let us integrate f of z along this contour consisting of L1, L2 and L3. L1 and L2 are along the arms of the sector and L3 and L2 is the portion of the circular arc. Okay. Alright, so let us integrate f of z equal to z to the power k e to the power minus z around a sector joining origin r and r e to the power I theta, where the angle theta is just the argument of s minus a. The figure explains everything. What does the Cauchy's theorem tell you? When a function is analytic, this function is analytic in the whole complex plane. So, integral along the closed contour will be 0. Integral of fz dz along L1 plus integral fz dz along L2 plus integral fz dz along L3 is 0. Okay. Now, let us look at these, let us examine these three pieces individually. Let us examine these three pieces individually. Integral of fz dz along L1 is 0 to r t to the power k e to the power minus t dt. And as r goes to infinity, what happens? You get the gamma function, gamma of k plus 1, correct. I think I made a mistake here. There should be a e to the power we are computing e to the that's okay. This is okay. It's gamma function. This is perfectly okay. Sorry. So integral of fz dz along L1 is 0 to in r t to the power k e to the power minus t, perfectly okay, converges to the gamma of k plus 1. Yeah, it's absolutely fine. We have no problems. Let us look at the integral along L3. Let's go back to the slide. Let's go back to the picture. What is L3? Along the second arm of the sector, right? How do I parameterize this L3? L3 is going from is coming towards the origin, right? So minus L3, if I look at the negative of the contour, it will go from the origin out. So how do you parameterize minus L3? Minus L3 you simply parameterize as t going to t into s minus a. You take a complex number and what are the multiples of the complex number? Tz, and t is bigger than 0. What do you get? A ray passing through the point z, no? So my complex number is s minus a. So look at t times s minus a. That's the parameterization for minus L3, the reversed arc, the reversed ray with the opposite orientation. Change the orientation, first parameterize minus L3. What is the parameterization? T going to t into s minus a. T will run from 0 to that particular point. Where is that particular point? R upon mod of s minus a. Remember, s minus a is not a unit vector. I have not used the unit vector along the. So my parameterization for minus L3 is simply t times s minus a, where t runs from 0 to r upon mod s minus a. Is that correct? All right. So let us look at integral of L3 fz dz is minus, where does the minus sign come from? Because I had changed the orientation. Minus integral 0 to r upon mod s minus a into, instead of z you are going to put t into s minus a everywhere in the definition, correct, and that is what you get, t into s minus a the whole raised to the power k e to the power minus t into s minus a. And now I am going to allow r to tend to infinity, and minus sign of course remains, the s minus a to the power k plus 1 comes out, and where did this s minus a come from? Z is t into s minus a, so dz is dt into s minus a, that is where this extra s minus a comes from, and all in all you have s minus a to the power k plus 1 coming out of the integral, and you get 0 to infinity t to the power k e to the power minus t into s minus a. Remember, that is the integral we are trying to calculate. So integral, yes please, integral fz dz L3 converges to minus of s minus a to the power k plus 1 into integral 0 to infinity t to the power k e to the power minus t into s minus a dt. Now there is one more piece remaining, right? L2, that is being left as an exercise for you. Show that limit as r tends to infinity, integral fz dz over L2 is 0. It's an easy exercise, please do it and take this seriously. Yes? Now go back to the equation, integral over L1 plus integral over L2 plus integral over L3 is 0. Let r tend to infinity. The middle term goes to 0. The first term gives you gamma of k plus 1, the third term gave you minus s minus a to the power k plus 1 times the integral that you want, correct? All right. So, that is exactly what we get, gamma of k plus 1 minus s minus a to the power k plus 1 into integral 0 to infinity t to the power k e to the power minus t into s minus a dt equal to 0. Therefore, whatever integral that you want, namely integral 0 to infinity t to the power k e to the power at e to the power minus st is gamma k plus 1 upon s minus a to the power k plus 1. Therefore, the Laplace transform of t to the power k e to the power at equal to gamma of k plus 1 upon s minus a to the power k plus 1. This is the correct argument. The other argument, put t into s minus a equal to u, is a wrong argument, despite the fact that it gives you the correct answer. The fact that it gives you the correct answer is irrelevant. That argument is wrong. This is the correct way of going about it. Well, so far what have we assumed? A is complex, and for simplicity we started out making an assumption on k, namely that k should be a non-negative integer. 0 is allowed. 0 is allowed. Now, you would like the k to be a real number, but then what is your f of z? F of z is z to the power k e to the power at. Take k equal to half or take k equal to 1/3. Then what is the function f of z? F of z will be z to the power half e to the power z, or z to the power 1/3 e to the power z, whatever, something like that we are going to get. What is that z to the power half or z to the power 1/3 going to do? Origin will no longer be a point of analyticity, correct? Origin will not be in the domain of analyticity of the function. So, the sector cannot have its end, its vertex at the origin, because at the origin it is not analytic. So, what do? What is the trick? You make a indentation, right? Small, cut out a little arc around the origin. You have the big arc L2, make a little arc of radius epsilon. So, now your contour has 4 pieces, 2 straight line segments and 2 circular arcs, and then you have to do that, and you have to go around that, and then you have to show, and then integral over L2 already you have proved it goes to 0, that stays. Now, you have to show that the integral along the little arc also goes to 0, that is also easy, and the result will continue to hold. The result continues to hold. So, if you do the indentation business, the contribution from the indentation vanishes, the formula continues to hold as long as k is bigger than minus 1. The moment k becomes equal to minus 1, the integral does not exist anymore. It does not, the improper integral no longer converges, and the Laplace transform does not exist. So, the formula Laplace of t to the power k e to the power at equal to gamma k plus 1 over s minus a to the power k plus 1 makes sense when a is complex and when k is bigger than minus 1. Of course, now the next thing would be to allow k to be complex, but let us not get into that. Let us just stop here with k real but bigger than minus 1. That is enough for our purpose. Let us not make it too complicated. And here are some exercises for you. Compute Laplace transform of t cos omega t, t sin omega t, t squared cos omega t, t squared sin omega t. Now that we have proved this formula, you are allowed to use it. You are allowed to use. We have proved it, correct? Calculate the Laplace transform of t squared e to the power minus at sin bt, cos at cos at, e e to the power minus t sine square t. Just write the functions, don't just write a list of functions of whose Laplace transform you have to calculate. And then write down the last one also. Laplace of e to the power at cos bt is s minus a upon s minus a the whole squared plus b squared, and b upon s minus a the whole squared plus b squared. Correct? Come on, please hurry up, please. Why is z to the power half not analytic at the origin? Suppose if it were analytic at the origin, its derivative will also be analytic at the origin, and hence will be bounded in the neighborhood of the origin. But what is the derivative? 1 half z to the power minus half, it is unbounded at the origin, so it cannot be analytic at the origin. That's one simple explanation. Yeah, it's one can give a geometrical argument also. That is when you go around the singularity, the determination changes and the square root changes its sign. We will discuss that later. That's proper complex analysis. I am not going to touch upon that during the course. Convolutions will be studied later, absolutely. Yes, we shall study convolutions later. Any other questions? Yes? Why is z to the power half not analytic? We can discuss at t if you like, or we could discuss it in the tutorial class, not in the lecture class. And what you're discussing, what you're trying to say is a Riemann surface for root z, that again should be discussed in the complex analysis course proper. We could discuss it at tutorial if you like.